Okay,
Yeah.
great. So I start when you want, actually. Should I start now?
Just a
I mean, we can wait for a couple of minutes.
We can wait for a couple of minutes. So in
Yes.
and hope my computer. So when you want, actually. So I hear my own voice. This is horrible.
Can wait for a couple of minutes.
We can wait for a couple of minutes. So in and hope. Okay.
Where is this sound coming from? Is it YouTube Live?
Yes.
Purvita? Yeah. Okay.
Now I cannot see my Zoom. Where is my Zoom? Went.
Tak. Aj. Finite. Aj. Okay, this works.
Shall we start?
Yeah, I think that's the best time to start.
Should I start?
No. So.
Okay.
No, he will share and then.
Yeah. So very warm welcome to this Logic webinar. It's our great pleasure to have Professor Friedrich Wehrung from University of the Caen. He is a CNRS research director at LMNO Laboratory, University of Caen. He belongs to the Graal team working on lattice theory, and also he is the editor chief editor for Algebra Universalis. And yeah, today he's going to talk about purity and freshness in categorical model theory. Over to you.
Thank you, Amit. So thank you very much for inviting me to Kanpur. And okay, so what I will tell you about today, I'm going to tell you not about lattice theory, but more about logic today. And so the references or the kind of categorical logic it involves is the one shown in the book by Adamek and Rosicki, which you perhaps know if you are category theorists. So I'm not myself a category theorist. I'm just an end user of it. And this is what I'm going to show you today, some end uses. And so some references of the for the techniques I'm going to show. I'm not going to show much technique today. It's going to be quite an elementary talk, just an introduction to some of the methods, a very elementary introduction, yeah, I would say. So there is a paper of myself with Pierre
from the future.
Pardon me?
There is a paper from the future. 2029.
No. I also got the. It's
no.
Right number. 2011.
Right.
I also got the future paper.
It is 2011, right? The date. This is the number of the issue.
That's right.
So it is paper of my former student Pierre Gilibert and myself. It is a book, actually. And mostly it is going to be about this paper, my recent paper on non-commutative diagrams and anti-elementary classes, which was recently accepted. And so all of this stuff, I mean, the references 2 and 3 can be downloaded from my webpage. And so what is the purpose of all this pain? So I want to prove that I have certain classes defined mathematically. They are not necessarily in lattice theory or in logic, or they can be in various fields of mathematics. And I want to prove that those classes are intractable. So examples. So I consider all rings not necessarily commutative. And I want to recognize, to be able to say when a poset is the poset of all like ideals of a ring. Is there a simple way to express this? Or other example, I have an ordered group, partially ordered abelian group, and I want to say, to be able to recognize when is it the K0 group of a unit regular ring. So, or now let's move to the realm of lattice ordered groups. So I want to know when a lattice is the stone dual of the spectrum of an abelian lattice ordered group. And so it doesn't matter if you know exactly the definitions or not, but because this is only a small set among many examples. So I want to prove that all those classes here are intractable in some sense. And a way to define intractability is to say the class is not like first order, or not even first order in an extended sense, meaning first order with respect relatively to infinitary logic. And so this is the kind of thing I'm going to show very, very roughly. So I would like to introduce a way to prove that certain classes are not expressible with infinitary logics of that kind, L infinity lambda. So I will say again what this is later, L infinity lambda. And so this is what I call anti-elementarity in my paper, and this is the kind of thing I'm going to use to prove intractability. So, and first let's get some motivation with some very well-known elementary concepts in abelian group theory. So if you are given a big abelian group B and a subgroup A, and a pure subgroup means exactly this. A intersect NB is an A for every integer. And so it means if the equation nx equals A has a solution in the big one, then it also has a solution in a small one. And so if the quotient is torsion-free, then this works. Proof is elementary. And wait a second, I'm going to check something. Okay, sorry. And okay. So every direct summand is pure. The converse doesn't hold, of course.
Sorry.
Yes.
Excuse me. Would you please explain what is NB or NA?
Yeah, it is the set of all nx. So it is
okay,
b plus b plus b plus b n times.
N is an integer. Okay, nx. Okay.
Yeah. So NA is the set of all n times an element of A. The set of all nth powers. Okay. So as you have seen, so purity is something about equation systems. And in fact, it can be expressed very nicely in terms of finite equation systems. So this is what I'm going to show now. So a finite equation system is this kind of thing, just a linear system, linear equation system. So the k's, they are integers, and the a's are elements in the group. Okay? And there is a theorem which is kind of well known. I don't know exactly who proved it first. It is older thing, that the subgroup is pure if and only if, when you have a finite equation system, if it has a solution in the big one, then it has a solution in the small one. It is kind of, so there is kind of retraction, but that retraction works only for finite equation systems. And it's very easy to prove, actually, because the integers is a principal ideal domain. So you have the matrix of all the kij's, and it is equivalent to a diagonal matrix because it works in this fundamental theorem of presentation of finitely generated abelian groups. So you can work with a diagonal matrix And once you have a diagonal matrix, then you are reduced to the nx equals a case. Once you have diagonalized. So it is elementary. And so now what I'm going to do is to extend purity to arbitrary first-order languages. So a first-order language, I don't know exactly how you guys are familiar with logic, so I gave a very short summary of a first-order language is a set of symbols of function, of relation, and with an arity function. So the arity sends every function or relation to a non-negative integer. And the relation has always positive arity. And the elements with arity, the functions with arity 0, they are just the constants. And to add to this, we add some infinite set of variables, an alphabet. And a model is just a set, a non-empty set with a bunch of interpretations of the relations of the functions and of the constants in a very natural sense. So the terms, okay, I just received a message from Purbita, so I guess it's redundant with what we have now. And so the terms are finite compositions of the functions. And atomic formulas are just express relations or equality between the terms. And first-order formulas are obtained by closing the atomic formulas under meet, negation, and quantifiers. Okay. And now a formula with parameters is just a formula with an assignment of the free variables. And satisfaction is defined inductively, the usual way. And now, elementary equivalence of models is a concept a bit weaker than isomorphy. So two models are elementarily equivalent if they satisfy the same first-order formulas. Okay. So if the structures are finite, it is just the same as isomorphy, but in the infinite case, it's not the case. So an elementary embedding is a bit more. You say not only elementary equivalence, but you say that you have a small model A and a big model B. And elementary equivalence holds for all formulas with parameters from the small one. So it is more than an embedding. And okay. Now, okay, homomorphism. Okay, you can observe that if A satisfies phi, then B always satisfies phi of Fa. I mean, you can always go from the left to the right if F is an homomorphism. This is trivial, actually. The converse is not true. And this is where pure embeddings kick in. And what is purity for first-order languages, first-order logic? So what I define now is an extension of the concept of an equation system. So instead of calling it an equation system, I call it an atomic system. The reason for this is that you have not only equality, but also relations. Okay? So it's a set of atomic formulas with parameters. And so again, what I was saying before, that if an atomic system has a solution in the small model, then it has a solution in the big model if you have a homomorphism from the left to the right. So existence of a solution of an atomic system is preserved under homomorphisms. So this is trivial. There is nothing deep there. And purity says that the converse holds. Okay. So purity, a homomorphism is pure when satisfaction of an atomic system is the same on the left and on the right. It deals with a non-trivial direction. So if you decode everything, like with the example with a billion groups, you can see it is the same actually. So this is just a complicated way to express purity for arbitrary first order structures, not only abelian groups. Okay. So this purity means that, so A, the small model, is pure in the big model, if and only if for every finite conjunction phi of atomic formulas. So if phi has a solution in B, then phi has a solution in A. And so for abelian groups, it's just the same as we saw. And there is a very, now I have a statement here. This is something, I guess, it appears in print for the first time in Adamek and Rozhitsky, and probably it can be found in Gabriel and Ulma and earlier references. So at any rate, this is again an elementary result. And it is a way to express purity in categorical fashion. Not mentioning what models anymore, just arrows. Okay, so it is purity without elements, just category. So purity means the following thing. So again, I want to say that the small model A is a pure submodel of B. So F is a pure embedding from A into B. This says more or less that A is a retract of B up to finite structures. It means, so if I approximate the embedding from A into B by a finite embedding between finitely presentable structures, then I can retract. There is a way to go from B prime to A. So there is a map G here that goes from B prime to A that makes the natural. The diagram doesn't commute here, but the left part commutes. So A is G composed with F prime. So don't worry if you don't see what it means. What I want to say is that purity can be expressed in a purely categorical way, not mentioning elements anymore. Okay. So by the way, so in my previous in this definition, I mentioned finitely presentable. What is finitely presentable? You are working in category theory. You no longer have generators and relations. Okay, so you're an arbitrary category. So finite presentability is just a lattice theoretical analog of the categorical analog of the lattice theoretical concept of compactness. So finite presentability of C means that whenever you have a map, an arrow from C to a directed colimit, then it factors through one of the SIs already. So it looks a bit weird again if you have never seen this before, but it is just really, it is just a translation. It is just a symbol shuffling. It is not completely trivial either, but it is well known at any rate. What does it bring? Okay, I don't know if you, for example, if you have the concept of a finitely presentable group, usually with a finite number of generators and relations. What happens if you want to prove that every retract of a finitely presentable group is finitely presentable? Then you shuffle symbols and it doesn't completely work at first because there are some complications. And once you figure out the exercise, it is not a trivial exercise to prove that the retract of a finitely presentable is finitely presentable. But it goes very smoothly when you use the categorical translation. Otherwise, it is not completely obvious if you try. Okay, so purity is a categorical concept, and this can be extended to lambda purity. Lambda is an infinite regular cardinal. So lambda purity is just the same as purity, except that I replace finite presentability by lambda presentability. So now we don't have directed colimits anymore, but lambda directed colimits. So it is just the same definition as before, with a lambda presentable instead of finitely presentable. And so it is a stronger concept. The bigger lambda is, the stronger is lambda purity. And so it can be again expressed in terms of small atomic systems for models. It gets stronger as lambda increases. So if you take a lambda, if you say that lambda is really very, very, very big, it goes to infinity, then lambda infinite purity is just existence of a retraction. It's just means that F has a retraction. It means a categorical left inverse. Okay? And so we need a stronger concept. So purity, I define purity. Now I'm going to define freshness. Okay? And freshness is an attempt to capture elementary embedding. It is a strong categorical statement that implies that the map is an elementary embedding. And it is, so what I'm going to show now, it is not the only way to do it. There are other ways originating with Pfefferman in 1972. But for my purposes, it was more convenient to use this one. I don't claim it is the only thing that would work, but it is just a possibility. So freshness is almost the same as purity, except that I require one more thing, which is an automorphism of B. So when I show the picture, we start with the same picture. A and F from A to B is the original map. So F prime from A prime to B prime is the small map that approximates it. And I want to, so purity says that there is a G that retracts B prime and to A in some sense here. And so freshness means that I require an automorphism S. There is a special automorphism S of B that somehow does the retraction. How does S work? So S, what it does is whatever was not in A and that we need is collapsed into A. So S collapses everything possible, everything we need to A. So we cannot say that S maps B into A, but it maps everything we need from B into A. This is the intuition of it. And so now, so you're going to forget the definition of freshness. It doesn't matter. It just remember that it's categorical, okay? And so what I will do now is to apply this to a special class of arrows and morphisms and categories. And the category I'm having in mind is the symmetric category over a set. So symmetric category is just some analog of symmetric group on a finite set, on a set. So a symmetric category, I denote it like this. It is not easy to pronounce. Inch of omega, I would say. And so the objects of the symmetric category are just the subsets of omega. Okay. And the morphisms, the arrows, are the one-to-one maps from X to Y, where X and Y are two subsets of omega. So F might not be, F is a partial function. F is a partial function. It is one-to-one. It need not be surjective. Okay. So this is my symmetric category. So the only compositions, I mean, you need the domain of one is the codomain of the other. And so it is as usual. Composition is defined as usual. And the directed colimits correspond to directed unions. So this category doesn't have all directed colimits because of success cardinal. This is an exercise. But it has all the directed colimits we need, which is going to be sufficient. So the directed colimits are just what you need to know is that they correspond to directed unions. Okay. And so a subset is what is the translation of lambda presentability now. Lambda presentability means it is just lambda smallness. Cardinality is small. So, okay. And yeah. Okay, so now what does purity, how do purity and freshness work on this symmetric category? It is again a small exercise. It is very easy, and freshness and purity are equivalent, and they are equivalent to either the trivial case, where F is a bijection, or the set A is large. And how does this work? You have, most of it is trivial. There is a small interesting direction. So we suppose that F is the inclusion map from A into B. And we suppose that A is large. And so we are given a subset of B prime of B, which may not be contained in A. And we need to find a permutation that is identity on a subset and collapses. It means what sigma should do is move as little thing as possible. Sigma should be almost the identity, but everything which is not in A is collapsed into A. This is how it works. And this we can do because B prime is small. So there is enough room to do this. So once you decode all the symbols, you see that it's actually trivial. There is nothing deep there. And there is enough room, yeah. So what I will do now is relate those concepts to infinitary logic. Okay. So what we'll do is a small reminder of what is infinitary logic. So infinitary formulas are defined in that fashion over first order language. And they are just defined the same way as first order formulas, except that we allow infinitary conjunctions, disjunctions, and quantifiers. So the first symbol, the first cardinal kappa, is a strict upper bound on the number of conjunctions and disjunctions you are allowed. The second cardinal parameter, which is smaller, is a strict upper bound on the length of the quantifier strings. So instead of saying there is an element X, you say, for example, there are omega elements Xi. I will give examples of this. And so if you, I will mostly consider the case where the first parameter is infinity. Infinity is some weird guy who is bigger than all cardinals. It means that I have no restriction on the number of conjunctions or disjunctions. And so ordinary first order logic is L omega omega, okay? Omega is the first countable ordinal. Okay, I gave examples that outside first order logic. So a finiteness, you have a set. The only relation symbol on this set is equality, okay? You have no ordering or whatever. And the finiteness of the set, so I use this symbol just to show its iterated disjunction. So it means that you have iterated disjunctions over all the integers. And so you say that there are elements, there is a finite number of elements, xi, such that every x is equal to one of the xi. So this is finiteness. So this is not a, if you follow the class in logic, you know that finiteness cannot be expressed in first order logic. This is one of the basic applications of compactness. But it works in L omega 1 omega, in this small extension of first order logic. Well-foundedness. So a pose that is well-founded, if it has no, you can say that it it is well-founded if it has no infinite, strictly descending sequence. So this is what I say here. It means for every sequence, xn, it is not decreasing. So there is an index such that xn plus 1 is not smaller than xn. So this is well-foundedness. So the first omega 1 here corresponds to the infinite disjunction here. And the second one, omega 1 here, is the number of the length of, is a strict upper bound on the quantifier. So omega 1, omega 1. Torsion freeness of a group, again, say that you have to say that for every, so iterated conjunction now, for every integer, positive integer, so the formula xn equals 1 implies x equals 1 is satisfied. So you don't need many quantifiers, so omega here, but you need an infinite conjunction, so which is the omega 1 here. Here are examples. And now from freshness to elementarity, so for any first order language, let me denote by structures of sigma, the category of all sigma structures. It means all the models for the language sigma. Okay, so to every symbol of relation, you associate a real relation. To every symbol of function, you associate a function. To every symbol of constant, you associate an element of the model. This is a structure. And this is a category. And so the models are the sigma structures. The arrows are the sigma homomorphisms. And so some results. So again, it is not difficult. So we are given an infinite regular cardinal and a first order language. So every lambda fresh homomorphism is an elementary embedding with respect to the language, to the infinitary language L infinity lambda. This is not difficult. There is a small point at the beginning of the proof. Okay, so what does this say? A is a fresh substructure of B. I skip the lambda. Okay, it means that the inclusion from A into B is elementary with respect to L infinity lambda sentences with parameters from the small one. And it is proven by induction on the complexity of phi. There is no surprise in this. It has a strange consequence that this works for phi atomic. So F is necessarily an embedding. It is one-to-one. It is a bit strange because the definition of freshness or even purity doesn't show any one-to-oneness. There is no monomorphism or anything. It doesn't belong to the assumptions. It belongs to the conclusions. So once you have said this, it is not difficult, but it's not completely trivial either. It needs to be verified. It is strange because we get the result that F is an embedding from purely categorical assumptions.
Right?
And yes?
If we just consider the lambda pure homomorphism, then how far we can go with this theorem? I mean, with the proposition.
It is also an embedding.
But not elementary.
It's not elementary, but it is elementary for PP positive primitive formulas.
Okay.
So this is in Adamek and Rojitsky's book. It is not completely trivial either, but it is, again, not difficult. Yeah. So if you have Adamek and Rojitsky's book, and yeah, so PP formulas. Sorry, I missed, my finger slipped. Yeah. So F is an embedding, yeah. And okay, I forgot what I wanted to say here from, okay. So what I would like to state now is a way to create lots of fresh morphisms. These are the ones I'm going to use. And these are created from the from the categories of the form inch of omega. And so I'm going to give an arbitrary category C and a functor from inch of omega to C here. And I want to say that this guy, that all the most arrows are sent to fresh embeddings. And this is a bit strange because, again, I'm not stating that that gamma of an arrow is an embedding, but this is going to belong to the conclusion, and it will just follow from lambda continuity, which is odd, but it's not difficult once you yeah. So again, so when you have a continuous functor from inch of omega to C, then it sends arrows to fresh embeddings, provided the domain of the arrow is large enough. It sends large arrows to fresh embeddings. And this is exactly what I say. So in particular, because of the previous result, fresh are elementary. So it sends arrows to elementary embeddings. And again, maybe I forgot to say, which inside, okay, so at the moment I wrote those slides, I was foreseeing that I would forget to define lambda continuity, indeed, so which is exactly what I do now. And continuity means that continuity of a functor, it means it preserves lambda-directed colimits. Yeah. So if x is directed union of xi's, then gamma of x is the directed colimit of the gamma xi's. Yeah.
Can I ask something?
Sure.
Yeah. So what if you, like, is there any other general class, like general category by which you can replace p inch omega?
Yes. Yes, you can. There is a garden variety. I just cry. This is just scratching the surface. I think it can. Okay, so in all the intractability results I proved, I just need this one.
Okay.
Yeah, and so I don't know, I have a dozen results of intractability, or I don't know exactly how many, and they all use those inch of omega. Okay. I think for further applications, something could be done with special classes of linear orderings, for example, with suitable maps. The suitable maps are not exactly, they cannot be lower embeddings, they cannot be initial segments. It is something a bit different, but I'm sure something can be done with linear orderings, and I think it is a very interesting way to world to explore, actually, especially with the linear orderings. Yes, good question. Yeah. And so, okay, for my purposes, I just need inch of kappa for the moment, but again, it is open to many generalizations. So now I say that the class of objects is anti-elementary if there are arbitrary large pairs of cardinals, lambda smaller than kappa, with lambda regular, and continuous functors, such that gamma of the small cardinal belongs to the class, and gamma of the large one doesn't belong to the class. And so, because of the previous results, gamma of lambda, the small one, is an elementary submodel of the big one with respect to infinitary language L infinity lambda. It is lambda fresh. And so C is not the class of model of any class of L infinity lambda sentences. So it is not first order. And there is a small catch here. Let me check whether, okay. I was a bit faster than I expected. So there is a small catch here, something that almost gets unnoticed. So I say that C is not the class of any modals, of any class of L infinity lambda sentences. So in particular, it is not the class of any modals of any single L infinity lambda sentences. So this sounds completely stupid, and you say it's the same, right? It is not exactly the same. So it means that if some strange class of objects C is the class of all modals of a large class of sentences, of L infinity lambda sentences, then it is not necessarily the class of all modals of a single sentences. You cannot always reduce a class of sentences to a single sentence. This is a bit strange. Let me give an example. I forgot to write it. And you have any class of ordinals. Every ordinal can be recognized by an L infinity omega sentence. This is a small exercise. So this implies that any class of well orders can be recognized by a class of L infinity omega 1 sentences. Any class of well orders. Because you just say that it does not satisfy the L infinity omega sentences satisfied by all members of the complement, something of that sort. So it is not completely trivial exercise, but it is quite interesting to go through. So it means any class of ordinals is recognizable by L infinity omega 1, but by a class. However, it is not always recognizable by a single sentence. For example, the cardinals. The cardinals are not recognizable by any single sentence. And they are not even an RPC, relatively projective class. No, with the rest. So they are not either RPC, cardinals. They are not RPC. They are not relatively projective with respect to any L infinity lambda. It is not completely trivial exercise, but it is a consequence of Löwenheim's column theorem. You have to prove a suitable version of Löwenheim's column. This is something you can do for a single sentence, but you cannot do for a proper class of sentences. But there is a catch, and it's strange. So, modals of a class is much more than modals of a sentence, of a single sentence. This is what I forgot to write here. So in this context, an anti-elementary class of objects is not the model of a class of L infinity lambda sentences. If I replace L infinity lambda by L infinity infinity, then it trivializes again, because any class closed by isomorphism would be the model. It would be the model class of an L infinity infinity class. Just consider all the L infinity sentences satisfied by all the guys not in the class, or something of that sort. So it is kind of optimal in that sense. There are more can be proved actually. So with a slight strengthening of anti-elementarity, I could prove that the class C in this context is not a co-RPC. It means complement of relatively projective class with respect to any infinitary language. For this, I need a proper class of inaccessible cardinals, which it is quite strange. We don't see the connection, but I couldn't get rid of the large cardinal. Okay, there is a whole world that ways to be explored there. That's what my meaning. So where does this gamma? So now what I did until now is just scratching the surface. I didn't say where this functor gamma come from. And this was the purpose of my paper number 3 in the list at the beginning of my talk. This is the real trouble, actually. The real difficulty is constructing the functor. This is difficult. And I go back to the example with finitely generated of rings, or non-stable K-theory of rings, or stone duals of spectra of lattice order groups, and so on and so on. Many examples. Okay, all those functors gamma are constructed using the same principle. So they need a deep exploration of those classes of rings and of lattice order groups and so on. And we have to construct non-commutative diagrams, special non-commutative diagrams of, it can be rings, it can be lattice ordered groups, it can be lattices, it can be many things. So we have to construct a special non-commutative diagram A. I'm not saying what is a non-commutative diagram, but it corresponds to intuition more or less. And it has to be this diagram A of, say, rings or lattice ordered groups, or this. It has, typically it is indexed by a cube, like all the subsets of a 3-element set, typically. And this diagram is so strange that it is not commutative. But once you apply the functor, phi is like the functor that sends a ring to its ideal lattice, for example. Once you apply the functor, it becomes commutative again. This is what I call phi commutative. However, this so okay, A is a bad diagram. A is a non-commutative diagram, and phi A is not isomorphic to phi X for any commutative diagram. It means that A is intrinsically, in some sense, non-commutative. And so it is just a rough intuition. The technicalities become quite more difficult here. And then what I need to do is using infinite combinatorial properties of P. P is the poset indexing the diagram. So in my previous examples, it's the cube or the subsets of a 3-element set P. It's a finite lattice. So the N that appears here is typically the order dimension of P. So the order dimension of the cube is 3. And actually, it has to be -1. 3 minus 1 is 2. This is why many counterexamples to this kind of representation problem have cardinality LF2. In fact, 2 is 3 minus 1. So yeah, and so I need using this those infinite combinatorial properties of the indexing poset. I construct a certain so-called a poset P of kappa, which I'm not going to define here, and what I call a p-scale Boolean algebra. So a p-scale Boolean algebra here is a Boolean algebra with an additional structure. This additional structure is a family of ideals indexed by the poset P, satisfying certain properties, which I'm not going to say here. And using this p-scale Boolean algebra, I build a complicated object in the category A. So this, if A is a diagram of lattice ordered groups, this is going to be a lattice ordered group. If A is a cube index diagram of rings, and this is going to be a ring. It's not going to be a ring. It's going to be the ideal lattice of a ring. Sorry. It is so it is a kind of technical object. So this is how the functor is defined, how the functor gamma is defined. Gamma of X is the p-scale Boolean algebra associated to X, kind of tensor product with A. So which is and yeah, I guess that's it. I was faster than expected, actually. Thank you very much for your attention. Thank you.
Many thanks.
Thanks a lot.
Yeah. Any questions?
Okay. I think there is some question.
Yeah.
Yes.
I'm not quite sure. Okay. So can you please go back to the last slide?
Yes.
Yeah, actually, I want to understand how can I think about p-scale Boolean algebra, because maybe I missed it when you were talking about. So how can I think it intuitively? So I can understand the role of that to preserve the structure of the algebra,
yes.
to make it work for the functor and all. So how can I think about it as a structure like p-scale Boolean algebra? So
Okay, so you know that Boolean algebras, they correspond to stone spaces via stone duality. P-scale Boolean algebras, they are in an extension, there is an additional structure. So the duals are also stone spaces. And to every ultra filter, to every element of the stone space, you associate, like if P is a finite lattice, you associate an element of P, actually. So every ultra filter has a norm, kind of norm that belongs to, essentially to P. And there are some continuity properties. Yeah. It's kind of a lower semi-continuous map. The norm is lower semi-continuous from the ultra filter space to P. Yeah. And this is the duals of those objects are P-scale Boolean algebras. Yeah. So they are. So we introduced them very carefully in our book with Pierre Gilibert, the reference number 2.
So it's very recent, that concept, P-scale Boolean algebra.
Yeah, we introduced it in 2011.
Okay.
In the book can be downloaded from my webpage. Yeah.
Thank you.
Thank you.
I have a question about this. So you mentioned that finitely generated ideals of R, yeah?
Yeah.
So if this is an example of intractable, anti-elementary class, then perhaps you can also prove that lambda generated ideals of R are also such examples.
Yes. Yes.
But is it true that like all ideals, like the collection of all ideals of ring, like I'm thinking about some kind of sequence of intractable sets which converge to some an elementary class.
So it's just the same, because the lattice, the ideal lattice of the ring, and the semi-lattice of all finitely generated ideals, they correspond to each other. Because because one is the ideal lattice of the other. The big one is the ideal lattice of the small one, and the small one is the semi-lattice of compact elements of the big one. So they are just the same. They correspond to each other via duality. Not duality, category equivalence, actually.
So even if you remove the finitely generated part, you still get intractability?
Yeah, because they are the same structures.
Okay.
Even for lambda generated or anything, you can go from one to the other. So it is so. And this is where categorical approach is interesting, because from category viewpoint, there is absolutely no difference between ideals and finitely generated ideals, because category equivalence. Thank you.
Any other questions? Okay, so let us thank the speaker again for this wonderful talk. I personally was quite interested.
Oh, thank you again. Thank you so much. Thank you. Thank you very much, you guys. It was my first Zoom talk. It is okay.
Actually.
It was really good.
One was excellent.
Well, you're very indulgent. Thank you, guys. Thanks. Thanks very much. So Amit, you are also Amit and Purvita, you are colleagues at the same university.
Yes.
Institute.
Yeah. Same.
At the same institute. Okay.
Yes.
Good.
So I was working with Jerzy Rozycki.
Oh, okay.
Yes.
So you know all the stuff very well. Much better than I.
Purity, yeah. And I was a student of Mike Prest. So perhaps
okay.
Yeah.
So he's a model theorist.